Now I'm delighted to introduce our second plenary speaker, Dr. Ruth Haas. Dr. Haas earned her bachelor's in mathematics from Swarthmore College and her master's and PhD in mathematics from Cornell University. She was the Achilles Professor of Mathematics and Statistics at Smith College for many years before joining the faculty at the University of Hawaii, Manoa, where she is now professor and graduate chair of mathematics. Dr. Haas is also the president of the Association for Women in Mathematics. Dr. Haas specializes in discrete mathematics and has many publications in the areas of graph theory and algebraic combinatorics. She was named a fellow of the AWM in 2018 as part of their inaugural class. In addition to her research expertise, Dr. Haas is known for her extensive mentoring of junior mathematician women. While at Smith College, she co-founded and co-directed the Center for Women in Mathematics, a program that later received the AMS Programs That Make a Difference Award in 2011. She also received the AWM Gwyneth Humphreys Award in 2015 for her mentoring of undergraduate women to pursue PhDs in the mathematical sciences. Indeed, Dr. Haas is very active in organizing workshops for junior mathematician women and doing collaborations with them to help them on their career paths. It is a great honor to introduce Dr. Ruth Haas.
Thank you, Christine. So I'm going to start. So I'm going to talk to you today about reconfiguration. And so what is, whoops, let me see if this works. There we go. So a problem can have many solutions. The word reconfiguration generally means to rearrange elements or settings. And in particular, we're going to talk about rearranging or changing between one solution to a problem and another solution to a problem. So as I said, this talk is about reconfiguring between solutions. So here's an example. So cat and dog, two lovely kinds of pets. Can you change a cat into a dog? Well, we'll just take the words. We won't take the animals. Can you change cat into dog one letter at a time? Well, let's see. You might go cat, dat, dog, dag, dog. Okay, well, that was easy. We actually should make it a little harder. What we really want to do is we want to change one into another, and at every step, have a good solution, have a real English word. Okay, so we want all real words now. So can you think of a way to get from cat to dog, one letter at a time, and every word that you have in the middle should be a real word. So here's a solution. Cat, hat, hag, hog, dog. Did you get the same solution, a different one? There's many ways, there are many paths. And so we've reconfigured, you can't see all my hands. We've reconfigured between cat and dog, maintaining good solutions, what we call feasible solutions at every step, okay? So in this talk, I'll talk about reconfiguring between solutions to a problem. And there's a variety of questions we ask. Can a feasible solution to a problem be transformed into another by an allowable set of moves while maintaining feasibility at all times? So that's the big fancy overview, right? And we did this with our English word problem. Can one English word be transformed into another by changing only one letter at a time so that at each step it's an English word? We could also ask, given some random two solutions, or like random two words, how hard is it to figure out if it can be done, right? Not even what's the solution, but is it possible to, how hard will it be to figure out if we can do it? And here's another question, given two solutions, given two words, for example, what's the shortest reconfiguration path? How quickly can we get from cat to dog, right? I had cat, hat, there's my shorter one, right? I had cat, hat, hag, hog, dog, I think. And I could have said cat, cot, dot, dog, even shorter, right? Can you find one even shorter? Okay, so you're plenty of things to keep you busy. If you get bored with what I'm saying, you can do my first name to my last name. See if you can find a short path between them. You can take any two good words. I should have looked at the names of some of the other speakers. Maybe you can do my first name, Ruth, to Alex's first name. That would be, I haven't done that one. All right. Pick your favorite two words as maybe your own first and last names. Okay. All right, so plenty of fun things to play with. So reconfiguring your life, configuring or reconfiguring your life, right? There's many ways to have a happy life. There are. It's not just one way. What do you want to do? I'm guessing you want to do a lot of different things. You want to have a happy personal life. Maybe you really want to get better at the kickboxing. Who was talking about kickboxing yesterday, Talitha? Maybe you want to be a mathematician. Maybe you want to have a family. Lots of things to do. How do you get there? Right? You're in a good place now. You want to get to another good place. How do you reconfigure yourself, right, from here to there? Is there only one way to do it? Do you want to do it the short way? I don't know. So here's a picture of some real people. 3 of them are real mathematicians. One of them is just playing a mathematician in the movies, right? So Hidden Figures down there at the bottom. Erica King, who hopefully is in the audience somewhere. I know she's at the conference, who is a mathematician, Hobart Williams Smith, and that's her daughter. She was a student of mine years ago. Didn't always think she was going to be a math professor. Pamela Harris, who is a professor of mathematics at Williams College and is a DACA dreamer. And she's a up-and-coming mathematician doing lots of really great things. And Maria Clava, who's a mathematician, who's also the president of Harvey Mudd College. So mathematician to leader, mathematician mother, family member, non-mathematician, but playing one on TV or on the movies, because, what else would you want to be, right? Okay, so let me tell you about me. Christina gave you the brief outline. I was an undergraduate at Swarthmore College, which is a very small liberal arts college, but a pretty elite one. And so I was a really mediocre math major. I was the worst math major my year. And when I told my faculty that I wanted to go to grad school, they were like, ooh, I don't know. Because usually only 1 or 2 of the students would go to grad school, and they would go to Harvard or University of Chicago. They'd go to these top places, and they kind of scratched their head. Well, you're not going to get into Harvard with your grades. You're not going to get into Yale. Maybe someplace you could go. Oh, who knows? So I went to Cornell. Yeah. And I didn't actually go in math. I was actually in operations research, which is a kind of applied math. It was a little less competitive to get into, quite honestly. It's more competitive now because it's related to financial math. But in any case, it's a kind of applied math, and a lot of discrete math is there into that area. It was, yes. And so I got my master's and my PhD there. And then, while I was there, I had a summer job at IBM, actually doing operations research, helping their operations go smoothly. Well, I thought I was helping. Probably I just had some silly summer job, but it was an interesting experience. It's my one experience in industry. And then after my PhD, I got a job at a big research university, North Carolina State University. And when I was there, the faculty, a senior faculty member said to me, teach your class and then close your door and do your research. Do not pay any attention to the students. I didn't really like that. That wasn't my thing. I wanted to, engage with my students. Teaching was a part of my job, and I really wanted that to be a fun part of my job and a valued part of my job. So I moved to Smith College, and I did a mix where I had a really nice mix of teaching and research. And that was great. So Smith is a women's college. I'll talk a little bit more about it later in my talk. And then after almost 30 years there, I started teaching when I was, -5, right? So after almost 30 years at Smith, I moved again, and I moved back to a big research university. And I said I stayed there almost 30 years. So I went back to a big research university and the University of Hawaii. If you want to know why I moved, it's actually usually very hard to move. When I was at North Carolina State back a million years ago, I met a significant other, and we got together. And even though we were in love and it was great, and we moved in together, we decided that I was really unhappy at NC State. It was not a good career move for me. And so I left one tenure track job and took another one. And we figured he would keep looking for jobs out. Smith is in New England, lots and lots of jobs, but that never happened. But we stayed together. So I had a commuting relationship for about 30 years, and we're still together. And you know, it's not the furthest ever. Lots of academics do this kind of thing. Lots of non-academics do this kind of thing too. Like if one of you is in the Navy and you're on the ship all the time, or if one of you is a long distance trucker and you're always on the road, or, right? There's lots of reasons people have commuting relationships. Anyway, we did eventually find 2 jobs together in Hawaii, and that's where we are now. So that's one of the reasons that I'm here, but it's also really different to be here at this stage of my career because people can't give me the same. I mean, I'm advanced in my career, so it's different to be here now, and I pay as much attention to teaching as I want to, which is a lot, as well as my research. Okay, so that's a little bit about me, and now let's do some math. So I'm going to talk about graph theory. I'm going to give you a mathematical context of reconfiguration. So let me tell you a little bit about graph theory. A graph is a bunch of dots or vertices, so a set of vertices, these are these dots, and a set of edges, those are the lines between them. So each edge goes between a pair of vertices. So for example, in this picture, I have the vertices 1, 2, 3, and 4, and the edges 1, 2, 1, 3, 1, 4, 2, 3, and 3, 4. And these can represent relationships between things, like this is a bunch of friends, a bunch of people, 1, 2, 3, 4, and there's an edge between them if they're Facebook friends, okay? And the drawing of it is not the most important thing. It's a nice visual representation, but it doesn't really matter where I happen to put the vertices. It's about the relationship between them. So it's okay for the edges to cross. That's not significant. It's just the way I happen to draw it. Okay, so this is the same graph drawn 2 different ways without the edges crossing in one case, but it's exactly the same graph, underlying graph. So we're going to talk specifically about graph coloring, and for graph coloring, vertices that share an edge must be different colors. So here I have colored actually every single, so 1 and 2 are different colors because they share an edge. 1 and 3 are different colors because they share an edge. 2 and 3 are different colors because they share an edge. Okay, and so an obvious question is, what is the smallest number of colors that you need in order to properly color this graph? And that's called the chromatic number, or chi of G. So what do you think? I'm looking out at the audience, but I can only see like 4 people. So what, for this graph, here I've colored it with 4 different colors, right? Green, yellow, blue, and red, but could I do it better than that? Could I do better? I say, peering out at you, and I see one person nod. Okay, so yeah, it turns out I could do better. I could do it with only 3 colors, right? I could have made this this red one down here. I could also make it yellow because it's not adjacent. It's not connected to the yellow one. So I could have done this in 3 colors, and it turns out I can't do better than that, right? Actually, this triangle here, 1, 2, and 3, they're all connected to each other, so they have to be 3 different colors. Okay, so there's lots of applications of graph coloring. You might have thought, well, this is amusing, but who cares? So sort of the most famous one is a map. If we take the map of the US, for example, and we say, if we want to color the states, you want states to be that are next to each other to be different colors so you can tell them apart. I should have memorized where Nebraska is, right? Here's Nebraska. So, so what we can think of this as a graph by putting a vertex for each state and then an edge between the vertices if they share a border, okay? And so Hawaii would be out here by itself. And then we want states that are next to each other to be different colors, which is why we've put an edge between them. So that's a problem, an application of graph coloring. And it turns out this is a very famous problem. It turns out that the answer is no matter how you draw your map, how we redraw the states, whatever gerrymandering, there's a whole other math talk there, right? However we redraw the states, we're only going to ever need 4 colors to color the map properly. But that's not relevant to us today. So here's another application, and it's this application of coloring to cell phone frequency assignment. Okay, so when you're on your cell phone calling somebody else, what is happening is that phone is connecting to some satellite on a particular frequency, which is just your conversation. And then from there, it goes to some other satellite, et cetera. But so basically you can think of every conversation is on a particular frequency, right? It used to be on an actual wire, but now it's on a frequency. And you want the frequencies to be different. If I'm talking to Christine and Colby is talking to Alex, again, I'm using the people who I'm looking at the moment. We don't want our conversations to get mixed up, right? You don't want to hear me saying to Christine, you know, Alex is looking a little peaked today. I wonder if he's feeling, you don't want to hear our private conversations, right? So you want the frequencies to be up. Sorry, Alex, he just put his video off. Ooh. So you want different frequencies, right? Except that, you know, if I'm talking to Christine and we're in Nebraska and Alex and Colby are talking and they're actually in Arizona, I don't know if that's farther enough away. They're talking on different cell phone towers, right? And so then it's okay to use the same frequency because they're not going to interact. So calls that are far enough away can both be red calls or frequency 5593 or whatever it is. Okay, so this is also a graph coloring problem. You have all your phone calls, and phone calls that are close to each other have to be different frequencies. And this is actually an online problem because it changes all the time. Online as in it's continually changing, and so you're updating. So you have to reconfigure how you're doing the coloring. Okay, so that's another application. Great, so let's go back to graph coloring. So in general, if I give you a graph like this picture in front of you, and I ask you what's the fewest number of colors needed, it's hard to figure out. It's hard to figure out how few you need, okay? So don't feel bad if you didn't figure out the other one quickly. In general, that's a hard problem. So that's chi of G again. And so, but you know, it's not our problem today. Our problem is gonna be if we have two good colorings, two good ways to do it, can we change the colors from one to the other in some nice way? Okay, so reconfiguration concerns the question, can we change from one good coloring, one proper coloring to another proper coloring? And so here's how we're going to think about this. We're going to make a graph of graphs. Okay, in math, we do this kind of thing all the time. If we take a theoretical problem, we make it more theoretical, right? We love doing that. So we're going to create what's called the K coloring graph of a graph. And so the vertices, so here my sample, my basic graph is just an edge, it's just a simple graph with two vertices and one edge between it. And I'm going to look at all the ways to color it using using up to 3 different colors. I have 3 crayons, I have red, green, and blue. So I could color it red, green, blue, red, blue, green, red. I think that's it. I only have these 3 colors. Those are all the ways to color with these 2 crayons, this single edge graph. Okay, so the vertices of my bigger graph are all the proper colorings. So all these 6 ways to color. And now I'm going to put an edge between if 2 colorings are different on just one vertex. Okay, so I just want to point out, because it's not clear always if you're new at this, that I'm thinking about the first vertex and the second vertex is different. So red green is different than green red, right? Those are not the same, because like one is the color I'm wearing and the other is the color that Alex is wearing. Okay, I keep picking on Alex. So right, so here's how we can change between colorings here. How do I change, for example, between red green and green red if I can only change one vertex at a time and I only have these 3 crayons? Well, I could, for example, take the first red one and make it blue, and then I would have blue green. That's why there's an edge here. Or I could take this, now I could take the second one, the green one, and make it red, and that's what I put that here. Or I could take the first blue one, or now, not for, sorry, make the blue one green. And so I could go here. So this gives me a path between these, right? And so there's another path. There's another way of doing it, just like there was many ways to get between cat and dog. And so here's another path. So there's no edge between these 2, for example, because both vertices changed colors, right? There's none between these 2 because, again, both vertices changed colors. So there's not edges between everything. I'm only putting edges where I'm allowed to change, right? So the thing about reconfiguration is that there are rules. You can't change everything all at once. right? That would be like, craziness. So you only want to change one thing at a time. Okay. Okay. So now let me give you one last application because it just makes me sound so sophisticated. This is an application to theoretical physics. This is the Glauber dynamics of the antiferromatic Potts model at 0 temperature. So antiferromatic, ferromatic like magnets, right? So this is things that don't attract, things that repel each other at 0 temperature because that just makes life better. Well, it's not quite that cold in Nebraska. It's certainly not that cold here today. The sun just came out and it's probably going to be like 80 degrees in an hour. Okay, so Glauber dynamics happen in systems like magnetism, lattice gases, spin glasses, and basically we have a bunch of atoms. And certain pairs must have different spins. They must be repelling each other. And so we're going to denote that by giving them different colors. Their spin values are their colors, right? And so if this is my collection of atoms, there's an edge between them if they have to have different spins, in other words, different colors. And the thing is that if you take a collection of atoms, a molecule, it might be in one state at one time and a different state at a different time. Or there's a variety of possible states that we see that molecule in. And we want to know, can you get between one state space, one kind of molecular state, and another one? Okay, and that's a reconfiguration question. And how long might it be for it to transfer from one to another? And this is about, doing chemistry and doing physics. So, right, so individual atoms can change spin one at a time. Otherwise, again, things don't just change all at once. And so like in this case, if I had the green, red, blue, red state space, then I might a bit later have the yellow, red, blue, red, because the first atom changed from a green state to a yellow state, okay? Okay, and so here's a part of the coloring graph for this particular base graph or molecular, whatever, configuration, okay? And you can just take a look at it and see what we have. Like we have that blue, yellow, red, yellow could change to green, yellow, red, yellow, right? And this gives you, these get very complicated very quickly, right? Okay, so let's go back to some questions. So a question that we have is how can we, what conditions do we need to ensure that we can reconfigure between any pair of colorings, okay? Maybe if I give you enough crayons, it will be true. Well, certainly that's true, right? Certainly if I can look at all the ways to color something with 4 colors and I give you 17 extra colors, you can always do a lot of extra color. I don't know, 17 might not be enough, but if I give you enough extra colors, you can just keep recoloring and eventually, right, you can keep your kid sister busy for a few hours until she finally gets to the right answer, right? So tons and tons of colors are going to make this easier. But what we'd like is not to need that many extra colors, right? How many colors in a box of crayons? Not that many, right? Okay, and so what you really want is you want that number of colors to maybe be with respect to the number of colors you need to properly color in the first place. That was that chi parameter, or maybe some other parameter about the graph, like the number of vertices. Well, that would be too big, but something, right? We want it in terms of some mathematical parameter. Okay, so let's take this one. So I can properly color this graph with 2 colors, right? Here I have green, red, red, and I could also color it this way, red, green, red, green. How can we get between them, right? Can we get between them using only those 2 colors? Is there anything I can color a different color if I start with green, red, green, red? I can't rechange the green to a red. No, I can't rechange this red, not rechange. I can't change the red to a green. I'm stuck at the moment. So I need at least 1 extra color, right? I need at least 1 extra color. So let's take 1 extra color. Let's take blue and we'll put blue here. So I changed the red to a blue. That's great. Now, can I keep going with just 1 extra color or am I going to need more extra colors than that? Well, it turns out I'm fine with just that 1 extra color. So first I made this one, vertex D, I made it blue, and then I made vertex B blue. And now that I have these 2 blues, I could make vertex A red, and then I made vertex C red, and then I changed back and got exactly what I wanted, right? So 1 extra color turned out to be enough here. So that was pretty great, okay? And so it would be really nice if it was always the case that I only needed like one extra color, or at least if the number of extra colors was a function of the minimum number of colors needed to color the thing in the first place. Okay, so let me give you another nice example. Okay, so here's a lovely graph. Let me explain this graph to you. So I have a bunch of vertices up here and a bunch of vertices down here. A vertex on the top is adjacent to almost everything at the bottom except the one directly below it. So this one here has an edge to all these other things here, but not to the first one. This one has an edge to everything, but not the second one. So there's no edge directly down, but there are all the other edges. Okay. How many colors does it take to color this in the first place? Just want to color it. Just one way to color it. Can you make all the top ones red? Sure, none of them are adjacent to each other. Can you make all the bottom ones blue? Sure, none of them are adjacent to each other. So the number of colors you need to properly color this is only 2, okay? So here's the question, are all the 2 colorings connected? Well, what are the ways to color this with just 2 colors? We already said red and blue, and you could also have gone blue and red, right? Can you get between those 2? Look, if all the top are red and all the bottom are blue, you can't change any blue to a red because they're connected to something above, and you can't change any red to a blue. So the 2 colorings are not connected. Same problem that we saw in the previous example. So let's take an extra color. That would be great. How about if I take 3 colorings, right? So if I have some reds and some blues on the top and all greens on the bottom, what can I do? Why did I have to have all greens at the bottom? Well, because they're adjacent to some of the reds and some of the blues, so they have to be different, right? So I can only use I have to use the colors sort of on different sides, right? Only on one side. And so if I have red and green, no, that's not what I said, red and blue and green down here, then what can I do? I can take the red and green and make them all red. And then I have all blue down here, and then I'm sort of back and I can play around with it. So it turns out that that's fine, yeah, with 3 colors. And so how about 4 colors? If I have like red and green and blue and purple, I can move them around. I can make everything up here the same color, and then everything up here down here the same color, and I'm all set. So that's fine. So why am I keeping talking here? What if I have M different colors? Yeah, sure, you can do it. Whatever, it's all good. It's all good. It's Saturday late afternoon for you all. Well, I don't know where you are. Now my friends at Hilo who are here too, or West Oahu. Okay, so there's an interesting M coloring here. Let me show it to you. Here it is, right? So remember I left out these vertical lines here, and that's so I can color both these vertices green, both these ones blue, red, purple, right? If I have M colors, then I can make every vertical pair the same, that same color. Can I change that? Can I change that back to all reds and all blues? What can I change? What's changeable without adding an extra color? Can I change this one? Well, it's adjacent to a blue, a red, a purple, a green, a chartreuse, a mauve, I don't know, pick your favorite colors, right? It's adjacent to all the other colors, so I can't change it. And there's nothing special about that. Everything is in that situation. Every vertex is adjacent to something of every other color. So this coloring is locked or frozen. It cannot be changed without adding even more colors. So that's crazy, right? We were doing great until I came up with this crazy coloring with a lot more colors than the minimum number needed, okay? So the minimum number of colors needed to color this graph was only 2. Chi of G was 2, but n+1 colors are needed to ensure that the coloring graph, that all the colorings are connected. So that's just bizarre, right? It's like weird things happen in math. We love that about math, right? Oh, wow, that's unexpected. And so this is why I used M here, right? You can make M as big as you like and have this problem. So the upshot of this is that it turns out that there's no function of the chromatic number. So not the chromatic number to the, or e to the chromatic number, or chromatic number factorial, or there's no function of the minimum number of colors needed that will mean for all graphs, you can always recolor with that function of colors, okay? So the chromatic number is just like not helpful in figuring out the reconfiguration problem completely, which is bizarre. So this was our example. This was our example that showed this because M could be as much bigger than 2 as we wanted. Okay, let me look at the time, which I can't see perfectly. Okay, so, right, so that was my example. So let me tell you briefly about something that does solve this problem. So finding the chromatic number, the minimum number of colors needed, is a hard problem in general. That's what I told you earlier. It turns out to be really complicated to figure this out. There's no good algorithms to do it. Here's something that's easier to find. So this is like a heuristic. In math, if we can't find the perfect answer, and we're doing applied math, then we want something that we can find more easily. That's useful anyway. That's pretty good, okay? So here's something called the coloring number. You have to bear with me for a minute. And so I'm gonna take my graph and I'm gonna spread out all the vertices just on a line, right? And I'm gonna put the edges between them here. And I wanna look at the degree of the number of edges out of each vertex that head back, right? That head back toward the beginning, okay? So the ones that go this way. I don't know if I can actually draw. Can I draw? No. Okay. Well, so the idea is that when I'm coloring this, if I color them by coloring this one, then this one, then this one, then this one, I only have to think about the vertices I've already colored. Okay. Whoops, wrong direction. So I'm going to start by coloring this color 1. I know it's a boring color, but it'll be useful that way. Red is color 1. This one can also be color 1 because it's not adjacent to the one right before it. The next vertex, well, it turns out it has edges to both of these two, so it needs to be a different color, color 2. The next one, well, it's got something to color 2 and to color 1, so it needs to be color 3. And I can keep coloring that way, so I keep coloring as I go up. And what's the worst thing that can happen? The worst thing that can happen is I have some vertex here, and it's adjacent to 7 things down there, so it must be the 8th color, okay? So the worst case is that I have to use one more color than the least back degree. You might think it's the biggest back degree, but it's the least maximum back degree under all vertex orderings. So it's the least maximum back degree, but I can reorder the vertices, right? I just plunk the graph down, try all the ways of plunking the graph down in a line like that. And so it's the least maximum back degree. It's a max min, a min max. We do that kind of thing in math a lot too, right? And so the point is that the coloring number, which is this other thing, is at least as big as the chromatic number because it's a way of coloring, but it's relatively easy to find, okay? So if you find the best ordering, you can color with coloring number crayons, okay? And so it turns out that that's the right answer to how many extra colors do you need in order to reconfigure your coloring, okay? So for any graph and any integer that's at least as big as the coloring number plus 1, there's a lot of plus 1s here. I want you to get the sense of what I'm doing, right? Not to memorize, there's no test. That's the great thing about a math talk. You just have to like say, oh, I kind of got it. That's kind of cool. You don't have to like learn the details. It's okay, no test. All right, so the coloring number will be connected if that's, the coloring graph will be connected, okay? Okay, so, and this was again, our example, the coloring number was M here, so we needed M plus 1 colors, and that turned out to be great. Okay, so there's lots of current work on reconfiguration of graph coloring and reconfiguration of lots of different things. And here's a picture of me and a lot of other people at a conference in Banff a couple winters ago. What's wrong with this picture? Yeah, look at all the men in it, right? Yeah, it's like, you know, this is a typical math. There are actually 3 women, but a lot of guys. This is typical, unlike the Nebraska Conference for Women in math. You know, this is what more like a typical math conference. Lots of guys, not that many women. So we're working to change that, right? That's why we're all here. Okay, so let me tell you about some work that I've done in this area. And some of the work that I've done is joint with some students that I had at Smith College. And so here's some pictures of students. I'm going to anonymize a little bit. I'll tell you some stories about people, but I won't tell you the story. I won't tell you the names and the stories at the same moment. So here are some former students: Carolyn Gardner, who was a master's in teaching student; Yoshi Marybird, who was a post-baccalaureate student. I'll tell you what that's about in a minute; Marissa Neal, Agnes Reck, who was also a post-baccalaureate student; and Nora Youngs. Nora, actually, I will tell you specifically about. So Nora graduated from Smith and went to the University of Nebraska to get her PhD, and she is now a professor at Colby College. So they did some work with me on reconfiguring of graph coloring. So let me tell you about the post-bac. So this is Nora here, actually. Let me tell you about the post-bac program. The post-baccalaureate program at Smith College. Here's the web address here. I think the slides are being posted. This is the web address has changed, so I don't know if you have the old slides or the new ones. Anyway, this is being recorded. So the post-baccalaureate program is a program for women who have bachelor's degrees, not necessarily in math, but it could be in math, who decided late in the day that maybe they want to go to grad school in math. And they decided that they maybe need some more preparation, or they want to be more sure that they want to do it. And so this program is now about 13, 14 years old, and women come for a year to Smith College. They take advanced level mathematics courses like real analysis, modern algebra, topology. They do some research. They hang out with a group of women for a year, all of whom are serious about math, which is great. They get advice about applying to grad school, getting their application material ready and where to apply and all that stuff. Anyway, and so it's a great program. So I'm not there anymore, so I can say that now, right? And it's the kind of students that we get in that program are both students directly out of college who, you know, thought they were going to be math ed, or thought they were English majors, and they, oh, now I want to go to math grad school, but they're not quite ready to be applying. So they come to Smith for a year. And it's also women who have done other things in the middle. So we've had women who were lawyers. We've had women who were architects. We've had women who, well, maybe I'll tell you as I go through some more pictures, but women who've had parts of other careers and then come back. So here's another picture of some post-bacs. This is at the joint meetings a few years ago, big math meeting. And why did I particularly want to tell you about this picture? So you know, there are a couple of faculty members in here as well. Right. This group of women, you know, it's really fun to go to a big general math conference with a bunch of women because you look unusual. Wow, look at that bunch of women when there are all these guys hanging around. And so I guess as happens typically at Nebraska, but not this year, we were all staying at the Embassy Suites, which is a great hotel, because they have these great big breakfasts, and they also have drinks and snacks at dinner time, which is really great if you're like bringing a bunch of students and you don't have a lot of money, right? So I told them, have a really big breakfast, put a roll in your pocket, you know, and here's where the free receptions are. And they would also go back and have drinks in the evening. So, you know, I mean, I know that you worry about maybe you're not the best math student in your class. Maybe, you know, maybe you think students are faster than you, or I don't know. There's many skills that turn out to be really important. So these students at the Embassy Suites in the evening were hanging around having drinks. I know this is not the best picture, but they're hanging around having drinks. And I come join them later and they say, oh, we just met these interesting guys and they bought us dinner. And I'm thinking, oh no, I don't know that I want to hear about this. Well, it turns out those interesting guys were the mathematical heads of the National Security Agency, the NSA, which is one of the nation's foremost employers of mathematicians. Shh, it's all a secret. And these guys, you know, they were very nice, fatherly guys. They came and they saw this young group of women. And they came and joined them for drinks, bought them pizza, because, you know, at the Embassy Suites, all you get is like chips and stuff with your drinks, right? So they, oh, and by the way, post-bac students are mostly over 21, so they were drinking legally, just in case you were all worried about that. In any case, the NSA guys came, hung out with my students. They had a really great time with them. Then the next day I met them because these guys from the NSA came to their talks, and they were so impressed by the poise and the verbal skills of the students. right? And so it's not just about the technical proficiency. If you're going to do math, you got to be able to explain it to other people, right? And that's what these students were really good at. And I'm sorry that I did not go to any talks this morning because it was before I get up in the morning, like here in Hawaii. But typically women give great talks, right? That your ability to give talks, even as undergrads, to explain yourself and to stand there calm and poised and to answer questions. These are super important skills, right? These are skills that will really help you get jobs. So among this group, there's a former architect who who said, I don't really like doing architecture. So I'm going to stop doing architecture. She came to our program at Smith College for a year. She met this guy at the NSA. She did actually go to graduate school afterwards. She went and got a master's in math. And the NSA just kept calling her, we're ready for you whenever. And now she works at the NSA, right? And there's also in this group is a former doctor. Actually, she was a med school student. She did 3 years of med school. And she decided, med school is just not for me. And she reconfigured. That's supposed to be my theme here, right? This is about reconfiguring. People, you can change your mind. It's okay. You can change your mind, right? It's okay to change your mind and decide to do something different, okay? She decided, I don't really want to be a doctor. She came to Smith for a year, and then she went to grad school, and she did math biology, which is perfect, right? It was the perfect, union of her biological interests and her mathematical interests, and now she's has her PhD, and I think she's in a postdoc still at the moment. Okay, so there's lots and lots of possibilities. Okay, so I'm going to change topic just slightly back to a little more math. All right, so here's another way of looking at the problem about reconfiguration. So we were looking at taking the two colorings and trying to go between them. We can also say, what graphs can you get that turn out to be the coloring graph of some other base graph? So we saw that the 6th cycle was the coloring graph of the little edge here, right? Of the little 2 vertex thing here, right? What other cycles? If I just drew a triangle, is there some graph where if I look at all the colorings and the ways to move between them, I would get a triangle? How about a square? How about a pentagon? How about an 8-sided cycle? How about a 20-sided cycle? What graphs can be coloring graphs, okay? That's another kind of problem, reconfiguration problem. What are the possibilities that could be reconfiguration graphs? Okay, I looked at that problem with this bunch of women, Julie Beyer, Janet Firson, Carl Lenhart, who's not in the picture, Heather Russell, and Kira Shavo. And all of these women are PhDs in mathematics. These were, not all junior faculty at the time of this picture. And so we looked at that problem. And let me tell you a little bit about some of their stories. Again, I'm not going to tell you who's who. 3 of them have children. I know that's important to some of you. Well, actually, 2 of them have children. One of them is about to have a baby, probably in a couple months. Yeah, she's pretty pregnant at the moment. One of them did a really interesting thing of, well, they're all interesting. One of them got her PhD at a normal age and got a tenure track job and was a professor, and then had children and said, you know what, I want to spend more time with my children. And so she stopped being a professor for a while and had children, had her children, raised her children. And then after about 10 years, when her children were pretty much didn't want her around all the time because they wanted, some privacy from mom, she said, okay, I'm going to go back and get another tenure track job. And so she did that and came back into mathematics after taking some time to be a mom. One of these women was an art major as an undergrad, did not do the Smith postbac program, was before that, but decided she really liked math, and really late in the day started taking extra math courses. I think she took them just sort of randomly at a local university, and then went to grad school, which was super hard, but she did it. And not everything is hard, by the way, but people do hard things, and it's okay. She went to grad school and she got her PhD, and then she went to one university with a job and she didn't really like it. And then she went to another one to see if maybe she just wanted to be at a different school. She didn't really like that. And now she's working at the NSA. That's actually pretty common, the NSA. It's a really great place to work if you want to do security kinds of things. They hire lots and lots of mathematicians. Okay. So anyway, that's, I think, enough stories about them. I am actually almost done, which I'm supposed to be. Oh, I want to tell you the answer to their question, right? So the answer is that the only cycles that turn out to be coloring graphs are the triangle, which is called C3, 3 vertices, the square, which is C4, and the 6 cycle, which you already saw, and that's it. You can't get a 5 cycle, you can't get a 7 cycle, you can't get a 10 cycle. Wow, kind of cool. Okay. Okay, so some life reconfigurations, right? So I'm a little boring. I did math. I mean, maybe my personal life is slightly less boring because it's more unusual. But I've told you about somebody who was a doctor or almost a doctor and then did math and then biomath. I told you about somebody who was an architect and then did math and then now works at the NSA. I didn't tell you, well, somewhere in the bunch of slides, there was somebody who was a sociology major and then decided to do math and then did sociology again. And now she's doing sociology of mathematicians and intersectionality of race and math and issues of inclusion. And then I told you also about somebody who did math and then was a mom and then did math. And not all of these are as disparate, right? These are not discrete. Life is not a discrete problem. I'm a discrete mathematician, as Christine said. Life is not discrete. Life is messy, and we enjoy the messiness. So what are my conclusions for you? My conclusions are there are many paths to a happy life. You can make choices and you can reconfigure when you need to. It's okay. Lots of us do it. It's great. So thank you and enjoy the rest of the conference.
Let's thank Ruth. I really enjoyed that, and it ends so positive. I'm excited. So it's time for questions. Let's still spotlight Ruth, I think. But let's take questions in the chat, or if you raise your virtual hand, I'll see if I can figure out how to call on you. Oh, there's one. Let me figure this out. Maybe I'm not good at this. Wait.
I have lots of answers to my how many colors are needed question from a while ago. I just noticed them now. I thought, why is 3 a question? But now I understand that you were answering my question from a while ago.
Emma Pickard has a question. Can we hear it? Can I unmute her?
Yeah. Can you hear me?
Yes.
Okay, thank you. Thank you so much, Dr. Haas. That was great. But I wanted to ask you, I had never heard about coloring like this before. It was really interesting to me. What are some further resources I could look into for just learning more about it?
So lots of intro graph theory textbooks will have something about graph coloring. And that's probably the easiest place to start. There's also a whole book called Graph Coloring, which will be a little bit more advanced. But you know, you can also use our friend Wikipedia, and you can look up the 4-color theorem. That's that basic problem that tells you that the map, any map, will need only 4 colors to color. And actually, that's got a really fascinating history because there were lots of false proofs. The first proof was really long and took a computer, but and people didn't like it because mathematicians didn't believe that a computer was really a good proof. They wanted, you know, those nice slick 5-line proofs, right? Or at least 5 pages. They didn't want a computer getting involved there. So that 4-color theorem is very interesting and famous.
Thank you.
Let's take Emily Cairncross's question.
Hi, thank you, Dr. Haas. That was amazing. And I loved hearing about so many different life paths. I was wondering, because I feel like in math, there's so many questions that some are like, they have a very specific application and some are just fun and most are like somewhere in the middle. So I was wondering for specifically finding which kinds of graphs can be like coloring graphs. Is there an application of that, or is it like a fun problem that maybe will have an application at some point in the future?
Yeah, it's really more the second. It's a fun question, but it's also, I mean, it's not just a fun question because understanding structural questions does pretty quickly lead to some important application, right? I mean, then you sort of have the parameters of what kinds of things could possibly happen, right? So the understanding which graphs is related to any time you want to reconfigure.
Thank you. Miriam, do you want to ask your question? Oh, let me see if I can unmute you.
Yeah, thank you. I really enjoyed the talk, and I have a little disclaimer is I had to step out in the middle, so I'm sorry if I don't know. I just wanted to ask if I'm sorry if you covered this, but I just wanted to ask, as you were talking about colorings, I was wondering, you had the square graph with the I forget two colors, and you said, well, can we get from one coloring to another? And I was wondering, does the answer have something to do, or could you interpret an answer as having something to do with like if you took a line and modified the graph to connect like the two vertices of the same color, or something, like how many lines you would have to add? Is that related to how many colors you would have to add to the graph to color it properly? Like, I'm not sure if I'm making any sense. Like in order to get from one to reconfigure to another.
I think I understand what you're saying. I mean, surely that's an interesting question. So it sounds like, I'm not sure. I'm not sure right away what the answer is. That is to say, yes, I bet it does have something to do with it. I bet there's some way you could say, okay, if you add this many extra, if you need this many extra edges to like different fuzzy edges, right? Fuzzy edges that are between two things of the same coloring, right? That's somehow telling you something about what's going on. But I'll have to think about that. It's an interesting question. Thank you.
Hey, Sally Smith has a question. She comments that a lot of these women did a neat job of combining different subjects with math in their careers, and she would like to know if you know anyone who's combined math and literature or art in an interesting way in their career.
Yeah, that's a great question. Okay, so math and literature, well, certainly being able to write and write a compelling story about your mathematics is very important, right? Because you know, it's not enough to have an answer, right? You have to be able to explain it, and also you have to be able to say, look, this is important, and here's why it's important, right? That's important because that you want people to fund your research, and you want to convince other people to get involved in your research. So you have to be able to tell a compelling story. So it's not really literature in that way, but being able to build your mathematics in a way that is compelling, that is good writing and good communicating, I think is critical. For art, there's actually a huge community of mathematical artists and artistic mathematicians. So if you Google math and art, there's lots of beautiful, beautiful art that uses lots of mathematics that again helps us see the math in a compelling way, but also just turns out to be beautiful art. So that's also really great. There are also some mathematicians who are mystery writers. I do know that in terms of the literature piece, right? And so it's sort of, you know, when you're writing a proof, when you're figuring out an argument and a strategy, you can also write a good mystery, I guess.
Thank you. Jillian King has a question. Have you encountered any research that suggests that all female colleges and universities, such as Smith, build more confidence in women than co-ed schools?
Yeah, so the women's colleges generally do have a higher percentage of science majors and women science majors than others. If you look at things like there's a study about the origins of people with PhDs, baccalaureate origins. So where people did their undergraduate degree who went on to get PhDs in certain fields. There's definitely an overrepresentation of women who went to women's colleges, right? Because they just, it was normal for women to do physics and math, right? So everybody who was doing it was a woman. Yeah.
Okay, Natalie Markich has a question. She first thanks you for the great talk, and then she asks, can you expand briefly on the Smith postbac program, particularly advantages of a women-centered postbac program?
Yeah, so so we were the first postbac program. They were the first postbac program at Smith. There are now a few others around the country. And the advantage, okay, so in my the way I like to put it is what you get at Smith is you get 3 things, maybe 4 things. You get coursework, you get connections because the program works to, you know, hook you up, let you get to know other people in the mathematical community and each other, and you get confidence because you're working with another group of women and feeling like you can do it. And so I think it is an advantage to see people like you who are going on in mathematics, who are serious. It reminds us that, oh, you know, there are lots of people who do this and they look like me, they are like me. And it also, you connect with this whole network of Smith women who have graduated and gone on to do all sorts of things in math, and they come back and talk to you and share their experience, and you're, you know, become a Smith sister. So I think it is an advantage, but there's lots of ways to do this, right? Just coming. So I was on a grant a few years ago with Judy Walker, who we met yesterday, who was one of the first organizers of the Nebraska conference. And there were a couple of other women who ran other women's only programs in mathematics, the EDGE program and the summer program for women in Minnesota. And, you know, all of us say that it's this sort of shot of feeling like you're just normal to be doing math and be female, you know, is really great. It's a great experience. And you get that here at this conference, you get that at the Smith program, you get that in the EDGE program. There's lots of ways to do it. It's not the only way to do it.
I'll briefly add that there are also math workshops for after your PhD where you can work on topics. And I met Ruth at a Women in Graph Theory and Applications workshop just a couple of years ago. Okay, Yuki Takahashi from Grinnell has a question. She says, when you have a partner who wants to pursue their own career, but who you want to live with, what advice would you give? Is it hard to choose a place to live as a professor? She's observed that many professors move every few years to find jobs.
Yeah, that's a great question. You know, you can't have everything in life. That's the bottom line. That's not the answer you want, right? I have a great life. I have a great partner. We've been together for 33 years, but we did not live together for a lot of that time. I mean, we did on the weekends. Every weekend, one of us would fly to the other one. Means we got to live in multiple places at the same time. We got, whoa, so many frequent flyer miles, unbelievable, you know, and so we get upgraded to first class all the time because we, you know, flew so much. Yeah, I mean, you know, it's because we wanted the jobs that we had, and we did look for some other things, but there were places we did not want to live. We made compromises. You always have to make compromises. I mean, everybody does, right? You may not see the compromise they make. You might make different choices than they would have made, but life is full of compromises. Academia is definitely a hard place to. It's very hard to say, I want this job and I want to live in this town, and I want my partner to also get the job that they want in this town. Academia makes that really hard, unfortunately. And, you know, right now with the COVID situation, academics is going to be even harder for a while. So, you know, I think the thing is that you have to think about what your priorities are, and you have to be willing to be flexible, and you have to be willing to do one thing for a while and then another thing later, maybe, right? You have to find a way to make it work, and nothing's perfect, but a lot of things are pretty good, even if they're not perfect.
Okay, I'm going to squeeze in the last question. So that everyone please stay on for that conference photo. So a quick answer to this last question. Christine Pereira from Wagner College asks, well, she first says your talk was very engaging, but then she wants to know what role did your IBM experience play in your career exploration?
Well, that's a great question. It convinced me that I did not want a job in industry, at least at that moment. It was an interesting thing to do, but it was, I don't know, it wasn't for me. I guess it was such a long time ago. It was fun. I got to meet different kinds of people. I got to work on a very specific applied problem. The kind of math, even though I did this applied math program, I do very theoretical math
for the most part. And I really love working with students. That's I think my passion. In fact, my favorite part about doing research is to engage others in projects. So my favorite part is not that what I get to prove and I'm really into this important thing. My favorite part is to work with other people and help them see their way in mathematics. So that's something that's, that's about academics. That's not about being in industry. But it was a really good experience. I mean, I'm still very glad I did it because I know something about what that world is like that is important, right? Important. As I talk to students, I can't say, oh, I have no idea. You should have an idea, right? You should know what the other half is doing.
All right, thank you so much. Let's thank Ruth one more time.